Hello, today we're going to talk about magnetic fields. A magnetic field, much like an electric field, can be defined as an aura that emanates through space, but unlike an electric field which emanates from a charged object, a magnetic field emanates from a magnetic object. So let's take a moment to talk about the difference between electric charges and magnetic poles, because they are not the same. In electricity, we talk about charges as having a plus and a minus. A positive charge, like a proton, and a, wow, if I could put these markers back, and a negative charge. We can have discrete isolated negative charges. We can have discrete isolated positive charges. And there is an electric field that emanates between these objects, with which we are quite familiar by now. I'm just going to finish drawing this one. A magnetic field, on the other hand, surrounds a magnetic object. So if I were to draw a magnet, it would have a north pole and a south pole, or a two-pole, apparently. Hopefully that looks like an S now. And a south pole. Like the electric field, the magnetic field absolutely travels around from north to south the same way positive travels to negative. In a magnetic field, the same way this positive travels around to that negative. But the difference is in the makeup. While we can have discrete positive and negative charges, we do not have discrete north and south poles. In fact, the makeup of this magnet is thousands of tiny little domains, or little north and south poles. So inside this magnet, I can find a bunch of tiny norths and a bunch of tiny souths, all inside this magnet. In fact, each electron inside of an object has what we call a magnetic spin. Each electron acts like a tiny magnet all on its own. So, if that's the case, and to our knowledge, we cannot split an electron, we also cannot split a magnet into single poles. There is no such thing as a magnetic monopole. So while you can find individual charged objects, you cannot find a magnetic north or a magnetic south in isolation. Where there is a north, you will find a south. Additionally, the magnetic field here between the charges goes from positive to negative. But inside the magnet, this magnetic field goes from south to north, creating a continuous circuit of magnetic loop, if you will. We observe these magnetic fields using iron filings in liquid to take a look at magnets and things like that. But what I want you to understand is that you can be magnetic and not be charged, and you can be charged but not have a noticeable magnetic field. And yet, every individual electron is in fact its own tiny magnet. The symbol you'll most often see associated with a magnetic field is a letter B for bemagnet. No, that's probably not why. So why is it a letter B? I have no idea. I don't know the reason for this letter, but what I do know is that the longer you work with magnetic fields, the more comfortable you'll become with calling it a B field. You'll hear it a lot from all of us. Magnets that have a permanent magnetic field to them are quite predictably called permanent magnets. Permanent magnets typically have a magnetic field of 10 to the minus 2 Teslas, Tesla being the unit of magnetic field, named after Nikola Tesla. The Earth's magnet is about 0.55 times 10 to the negative 4th Teslas. So it's not hard to imagine that a bar magnet would be more attractive to a compass needle than a regular magnet. So here's a magnet that I have here. And It is not on a level surface, sorry about that. But if I give it a little spin and let it sit for a little bit, it will eventually align itself to the Earth's magnetic field. Fun fact, the Earth's North Pole is actually magnetic south. We call it the North Pole because it attracts the North Pole on compass needle magnets. But in order for it to attract the North Pole of a compass needle, it actually has to be magnetically south. Process that for a minute. Much like electric charges, we have a certain set of rules that apply that are true for magnets as well. Opposites attract and likes repel. Positives attract negatives, negatives attract positives. In magnetism, north poles attract south poles and south poles attract north poles. So I have here a magnet that I am going to place on a stand. And if I let it sit for a little bit, it will in fact align itself to the Earth's North Pole. It will align itself with the Earth's magnet if I just give it enough time. It can take a little bit of time. Okay, we appear to be aligned to the Earth's magnet. But if I bring out another magnet, we can see this magnet react to it, right? We can actually also see this magnet pulling the magnet in my hand back and forth, right? And if I align it here, we can watch them both make each other a little bit crazy as they work to get their North Pole and their South Pole as close together as they possibly can. So bar magnets or permanent magnets tend to have stronger magnetic fields than the Earth's magnetic field, and so they tend to govern each other's behavior more readily than a lightweight little compass needle or the Earth's magnet. If every single electron acts like a tiny little magnet, what happens if we get electrons aligned in some way? What if we got electrons moving, say, with an electric field or a potential difference? What if we got electrons moving through a circuit? Would they align well enough to make a magnet? It turns out that yes, they do, and they do it predictably so. And so if I took current and I put it through a wire, I could figure out the direction of the magnetic field simply by putting my thumb in the direction of the current and curling my fingers around the wire. My fingers would point in the direction of the magnetic field. And we're very aware of this magnetic field because we have radio interference. The magnetic fields surrounding power lines actually cause radio interference for us when we're driving down the street and listening to the radio. For those of you that still listen to the radio, right-hand rule number 1 is, again, thumb in the direction of current, and your fingers will naturally curl in the direction of the magnetic field. So what if we took this wire with the current running through it, and we instead turned it into a loop? What would happen with those aligned magnetic fields? It turns out that those magnetic fields would continue to be there. However, now that magnetic field would be traveling all around the inside, all through the loop in the same direction. So we would have this concentrated magnetic field in the center. This is how we make an electromagnet. In order to figure out the direction of this magnet that we've made, we use what's called the second right-hand rule, where you curl your fingers in the direction of the current, and your thumb will naturally point in the direction of the magnetic field through the center of the coil of wire. A coil of wire will have a magnetic field surrounding each layer of the wire, which will generate a magnetic field that goes, a strong magnetic field actually, that will go through the core of the coil of wire. Now, we can't really, even though the magnetic field will be there, we can't really get a sense of it unless we can extend the magnetic field beyond the coil of wire using some piece of metal that is ferromagnetic or at least easily alignable. So I'm going to connect power supply that goes all the way over to that power supply back there. And I'm going to turn this on. Before I turn it on, you'll notice that I cannot pick up any paper clips. But once I turn it on, and try not to short the sucker out, you'll see it easily picks up magnets. Now this, or paper clips. Now this is without me doing a whole heck of a lot. This is not a particularly strong magnetic field that we're making right now. Now, while we're not terribly focused on math here in the summer program, we do want you to have some idea of how the strength of different aspects of the wire affect the strength of the magnetic field generated around it. For a straight current carrying wire, its magnetic field, which again is in concentric circles surrounding the wire, is made stronger by strong currents, which makes sense. If you get all the electrons aligned, moving faster and better, then of course they're going to make a stronger magnet. And as expected, as you move further out from the wire, that magnetic field is going to get weaker. Likewise, for a coil of current carrying wire, we find that stronger current yields stronger magnetic fields, but at the same time, more loops of wire will also give us a stronger magnetic field. And it turns out that since the magnetic field is strongest through the center of the electromagnet, we actually don't have to worry about how far we are from the magnet or from the wire, as long as we're in the core of the coil of wire. There's another constant sitting on there that you might not be familiar with, mu naught. It's known as the permeability of free space. What you need to know about it at this point is that it's a property of a vacuum. That's about it. We also deal with, in electric forces, the permittivity of free space. This is just, again, a property that is unique to a vacuum. It would have different permittivity or permeability depending upon the material we're working with. But since most of the time we deal with magnets in air, we call that close enough to a vacuum for our calculations. So, moving charges can generate magnetic fields, which means that a wire with a current in it can kind of act like a magnet. And a coil of wire, as you've seen with the electromagnet, can act like a magnet. So what if we took a wire and we put it in a magnetic field? We are already aware of the fact that magnets have effects on each other, that when we bring one magnet close to another magnet, it absolutely forces it to move around. So what would happen if we took a wire that had a magnetic field surrounding it and placed it in a magnetic field? It makes sense to think that, well, that wire would be moved by the magnetic field that it's in. And in fact, it turns out that it is. To determine the direction of this magnetic force, we use what's known as the third right-hand rule. It's really very simple. It's you put your thumb in the direction of current and you flare your fingers out in the direction of the magnetic field, and your palm will point in the direction of the force. So if I have a wire that's going upward, that's got current moving up in a magnetic field, and a magnetic field that's coming towards you, I would be pushing that wire across the screen. So here we have a long metal pole that's acting as a segment of a current carrying circuit. The top of the pole is connected to the higher potential end of a power supply. The lower potential end of the power supply is then connected to the bottom of the pole. The pole rests in the center of an existing magnetic field. As the power is turned on and the current moves through the circuit, a magnetic field is generated around the wire, and the magnet forces the pole out of the field. As we remove that magnetic field, the pole returns to its original position. If we reverse the polarity of this circuit so that current instead acts in the opposite direction, we will find that the pole is forced in the opposite direction. And again, for another view, as the power is turned on to this circuit, the existing magnet forces the pole out of the magnetic field. The pole has a current running through it that generates a magnetic field surrounding it. When the direction of the current in that field is reversed, we find that the pole gets pushed in the opposite direction. So in this particular case, my thumb goes with the current, my fingers go from north to south with the magnetic field, and the pole is pushed that way. If I reverse the polarity one more time, we will see that the current travels up through the pole, the magnetic field goes from north to south, and the wire is forced the opposite direction. So, how do we determine the strength of that magnetic force is the next question. Well, I like to summarize it as F Bill. That's nothing personal about our beloved Bill. But it is the magnetic field times the current times the length of wire that's in the magnetic field. Again, we're not super stressed about you knowing this math or anything like that. But it's worth noting that the stronger the magnet, the stronger the force on the wire. And the stronger the current through the wire, the stronger the force on the wire. And of course, the more wire in the field, the more force it's going to feel. This just makes sense. There is one math thing that I'd like to point out to you in all of this, and that is that calculating magnetic force is in fact what's called a cross product. It's a unique type of multiplication. So somewhere in your schooling, you learned pretty simple math. 3 times 5 is 15. As you got older, you learned that, hey, you know what? You don't really have to write that times sign. You could just write a dot. Or no dot at all. A dot 5 is 5a, right? But when you're working with vectors, a dot product versus a cross product, writing the dot versus the x actually means two very different things. So in example, if I take a force and I multiply it by a displacement, and I use a dot between them, these are both vectors, and I will get out of them work, which is energy. It's just an amount of something. It doesn't have a direction the way force and displacement have a direction. But if I take two other vectors, such as a magnetic field, and I cross that against a current, which also has a direction, I will actually get a third vector in a completely different direction, which in this case with my hand is coming out of the screen and towards you. How do we draw a vector that is in a completely different direction and is coming out aiming at you? Well, if a vector is coming at you, and a vector is basically an arrow, then you're looking at a point. You're looking at the tip of the arrow. If, on the other hand, I flipped this around and my magnetic field was down and my current was across, now my palm is facing this way, and now the force is coming towards me, which means that you would be looking at the tail feathers on the vector. So a dot means that a vector is coming at you, and an X means that a vector is coming towards you. This is very helpful when it comes to drawing magnetic fields because we tend to draw them going in and out of the page so we can visualize forces in other ways. Every charged particle acts like a tiny magnet, which means that they can be pushed around quite easily in a magnetic field. In this experiment, the cathode ray tube experiment, A beam of electrons is shot into a vacuum tube. At present, those electrons are left undeflected. But if I bring a magnet into the space, look what happens to the electrons. Each electron, acting as its own tiny magnet, is affected by the presence of a larger magnetic field. And in fact, if I flip the magnet, it's affected in the opposite direction. Each electron acts as a tiny magnet. It's actually this deflection that helped J.J. Thomson to determine the charge to mass ratio of the electron. What's different from a wire being forced around in a magnetic field and a charge being forced around in a magnetic field is that as the charge changes direction, the force will also change direction. So, an example, if we had a magnetic field, ooh, this takes a little while to draw. If we had a magnetic field that was coming this way, away from you and into the board, and we sent a positively charged particle into this field, heading this way. As that charge entered the field, it would be forced down as it entered the field. So I'll draw it right here so we can see it in the field. It will get forced down. But as it heads down, it will in fact now be headed this way. And now, boop, that force will likewise change direction. And the charge will change direction also. And the force will change direction, and so on and so forth. It's something very specific that occurs when force is perpendicular to the speed of an object. We have uniform circular motion. A charge in a magnetic field will sweep out a circular path. That's actually a very big deal to people like the high energy physicists that are working at CERN to identify particles, because they can actually identify particles based upon the size of the circles that they sketch out in the particle chambers. Positive particles will go one way, negative particles will go the other way. More massive particles will be more difficult to turn, so they'll make larger circles, and lighter particles will make smaller circles. Heavy charges, not heavy charges, but large charges will make tiny circles, and light charges or lesser charges will make larger circles. So this is actually very important, and this is actually something that is used in things like the mass spectrometer, which is used directly to determine the mass of charges, or the mass of known charges. And it's very important in directing charges through particle accelerators, in proton therapies, and things like that. This device, known as an E/M apparatus, in full light, you can see that it consists of two large coils used to create a magnetic field. Once that uniform magnetic field is created between those two large coils, a beam of electrons is fired into this chamber. Without the presence of the magnetic field, the electrons shoot straight up. With the presence of the magnetic field, the electron beam is able to coil around. By adjusting the strength of the magnetic field, the size of the loop marked out by the electrons is able to change size. So, you can quite clearly see this beam of electrons. Now we will shut off the magnetic field to the electrons. And you can see the electrons shoot straight up into the chamber, undeflected. But as soon as we turn on the magnetic field to those coils, the electrons begin to mark out a curved path. Now, we will adjust the strength of the magnetic field experienced by those coils, or generated by those coils. As it gets stronger and stronger, the beam of electrons gets put into a smaller and smaller ring. Though it's difficult to see, that little bright spot marked off by the electron beam is in fact a tiny measurement of the diameter of that ring being measured out by the electron beam. With that measurement and the knowledge of the strength of the magnetic field, the voltage and current through the coils, and the potential difference that is across the electron beam, or generating the electron beam, you can actually figure out the mass of an electron. Or turn it down, rather. And you'll see it hit another marker. And another marker. And if I turn the magnetic field up, we see still more markings there. So pretty cool, if I do say so myself. Other applications of this come along with the electric motor. If we can have a coil of wire that has a magnetic field running through it, and we can place that in another magnetic field, then we could get that coil of wire to turn in the magnetic field. And in fact, if we could get the current to change direction, then we could get it to force itself all the way through that magnetic field. And it actually turns out that that alternating current, that concept of alternating the current so that we could keep this coil of wire moving, is actually what led to the generator and the motor. Other applications of this include the speaker. A speaker cone has a large coil of wire at the end of it that is placed in a magnetic field. When current runs through the coil of wire, current that happens to be changing with the frequency of the music, it ends up forcing that coil of wire to move in the magnetic field at a frequency that matches the frequency of the music, which in turn shakes the cone at the same frequency as the music, which shakes the air, which eventually shakes your eardrum so that you can hear that music. If every charge acts like a tiny magnet, then those tiny magnets are affected by magnetic fields. We see charges getting forced to move, we see charges generating their own magnetic fields, and all kinds of good stuff. Next week, you'll take a look at if moving charges create magnetic fields, could magnets be used to generate electric fields, and all of the implications that come with electromagnetic induction. Thank you. No.
You sound very bored.
I am very bored.
Just say hello a little more enthusiastically.
Okay. Hello! Is that better? Today we're going to talk about magnetic fields. Is that better? Hello! All right. Hello! I can't even do it. All right. Hello. I can't say hello now. So messed up. All right.